Welcome everybody to the next video in our series on probability and statistics. I am Dr. Lathram, and today we will be talking about the F family of distributions. So to see where our F family actually fits in, let's review a little bit of what we've done so far with our hypothesis testing. So remember that conditions for our hypothesis testing. So for our z-test, we had independent, identically distributed random variables, y sub 1 up to y sub n, however many. In this case, we were looking for mu, but we had the variance actually known. And so the variance was known for either one or two groups that we had. For the t-test, it was kind of the same setup, but we had the variance unknown, but we only had one or two groups. Now, if we could further relax that condition on the variances for the null and the alternative hypothesis that the variances didn't even necessarily have to be the same. That problem is actually called the Behrens-Fisher problem, and it really is an unsolved problem in statistics. Now, there are approximations to deal with it, and we'll talk about those in a later video. But for now, we'll assume that our variances are going to be the same. And then finally, if we have a large enough sample sizes, so we're still assuming that we can use the central limit theorem, and really for all of the data that we will actually generate, they will be from normal distributions, then we may want to consider relaxing the condition on the number of groups that we have. So maybe we don't just have two groups, maybe we have 3, 4, 5, however many. And so we might be able to look at this and say, well, couldn't we just do multiple t-tests? And so let's explore that possibility for just a second. So suppose that we have a total of n tests that we are going to do. Now we've got the probability of type 1 error for each test being a value of alpha. And so the number of times x that we have type 1 error has a binomial distribution with parameters n and alpha. Well, that means that the probability for any type 1 error at all occurring anywhere is going to be 1 minus alpha to the n. And so if we just look at alpha being a significance level of 0.05 or 0.01, with n being 2 or 3, or by the time we get up to n equal to 4, even with a reasonable significance level, we've got the probability of any type 1 error being almost 20%. And so for those situations, because our type 1 error is just going to accumulate for the more groups that we have, this really isn't a viable solution for us to be able to do. So the multiple t-test thing isn't going to work out, so we need something else. And so what is that something else? That something else is a brand new distribution. And so the setup is this. We've got two random variables, independent variables, x and y. We assume that x has a chi-squared distribution with nu sub 1 degrees of freedom. Y also has a chi-squared distribution with nu sub 2 degrees of freedom. And we're going to define this new random variable f, capital F, which is going to be the ratio of those two. So x over nu sub 1 divided by y over nu sub 2. An expression that has this particular distribution is said to have an F distribution with nu sub 1 degrees of freedom for the numerator, nu sub 2 degrees of freedom for the denominator. And of course, not surprisingly, that's going to be how we denote our F distributions. So we're assuming that x and y are independent, and so what happens is that the joint PDF is just going to be a product of the marginals. But both marginals are chi-squared distributions, which will have the forms that we see here. Now, taking the product of those gives us this expression, which is a little bit long, a little bit complicated. So what we want is a transformation. So we want the cumulative probability distribution for something of the form y over x, being less than or equal to k. And so what we do, we come up with a transformation that will give us just that. Okay, so we'll consider the transformation where we have y is equal to u times x and x is equal to v. So that really the inverse transformation is u is equal to y over x and v is equal to x. Okay. So of course, taking the Jacobian of that transformation, we're going to just have negative v. And so if we look at the joint PDF, so here's our joint PDF in terms of x and y. We make the substitution, multiply by the Jacobian, do some simplification, and we end up with an expression that looks like this. And so we may not look like we really gained any ground, but let's look at the PDF for V. The PDF for V is actually from the gamma family of distributions. So it's a gamma distribution with a parameter for alpha being nu sub 1 plus nu sub 2 over 2 plus 1, and the beta being the scale parameter just being 2 over 1 plus u. And so that means that for the integral with respect to v, we know what that integral is going to be in terms of the gamma function. And so if we look at the probability of f being less than or equal to k, well, we can integrate over the v's, and so we end up with an expression involving u that looks like this. And so if we can pull the normalization parameters out front, and so we have an expression that looks like this. Inside we actually have something that looks like a rational function in u, but we can simplify that just a little bit more if we think back to a previous video that we did on the gamma function where we talked about the beta function. And so the beta function b of xy is going to be this expression, but we can evaluate the beta function in terms of the ratio of some gamma functions. And so what that lets us do is simplify our expression so that the probability that capital F is less than or equal to k is going to be 1 over the beta function at nu sub 1 over 2 and nu sub 2 over 2, and our PDF for our F distribution has the form that we see here. And so what we really want to take away from this, the important thing to remember, is where does the F distribution come from? The F distribution is coming from a ratio of chi-squared distributions. And so that's really the important thing. So anytime that we're looking to compare sigmas, compare variances, remembering those are distributed as chi-squareds, and so the ratio of chi-squareds returns us to the F distribution. And so it's natural to say, well, what questions does the F family help us to answer? And two actually very big questions. One of them has to do with hypothesis testing, where suppose we have two distributions and we would like to know if the variances are the same. So a situation where that might arise, we're actually comparing the precision of two different machines. We want to know if one machine is going to have a better precision, that is a smaller variance, than the second machine. The second case where the F family is going to come into play is in testing of means when we have more than two distributions. So kind of our beginning motivating example was what happens if we have 3 groups or 4 groups or 5 groups. We couldn't do the multiple t-tests because our level of type 1 error would just end up going through the roof, and so we need a different solution. Well, that solution is something called an analysis of variance, so an ANOVA. Now, kind of where would that naturally show up? Suppose that we have 3 groups in a medical experiment, and the first group is receiving a placebo, second group is receiving kind of the standard care treatment for the drug, and maybe our real test is we're testing a supplemental drug that enhances the standard treatment. And so really we've got 3 different treatments here, one for the placebo, one for the standard of care, and one for kind of an enhanced standard of care. So that's a pretty reasonable situation that we could be dealing with, where the multiple t-tests are not going to do the job for us, and we need something stronger with the analysis of variance. So now let's look at our hypothesis testing question. So we're the setup for that. We have 2 groups of independent variables. So we've got a bunch of x's and we've got a bunch of y's from 2 different distributions. So y's being from 2 different distributions. Our x values, we've got m of them from an IID distribution with a Gaussian distribution with mean of mu sub 1 and a variance of sigma sub 1 squared. The y variables, we've got n of those, and they are an IID sample from a Gaussian distribution with a mean of mu sub 2 and a variance of sigma sub 2 squared. And so our null hypothesis is going to be that the variances are equal. And so for the alternative hypothesis, we can have 3 different ones where sigma sub 1, the variance of the x's, is greater than the variance of the y's, where the variance of the x's is less than the variance of the y's, and then the third option where the variances are just not equal. So we have an upper tail, a lower tail, and a 2-tailed alternative. And so the statistic that we'll look at is the F statistic, where we're just looking at the variance of sample variance of the x's over the sample variance of the y's. And so our rejection region for the upper tail is going to be f greater than f sub 1 minus alpha. The lower tail where f is less than f sub alpha, and for the 2-tailed test where we have the absolute value of f being greater than f sub 1 minus alpha over 2. And remember that our F distribution is going to have an F distribution with degrees of freedom of m minus 1 for our x's and n minus 1 for our y's. And so now let's take a look at the second question that the F distribution helps us to answer, and that's going to be the ANOVA question, so the analysis of variance question. So the setup for that is that we have a collection of k different normal distributions. So these are all independent. From the ith distribution, we have collected n sub I IID data values. Again, these are all from normal distributions. We assume that the variances of all the distributions are the same, but we don't necessarily know what it is. So, and that's going to be an important thing, that we assume that the variances are all going to be the same. And so what we can do is we will put all of the observations together. So we're going to so-called pool all of our observations, and we look at the sample variance of the pool. So we've got s squared 1 over n minus 1. We're summing over all of the groups. We're summing over all of the elements in the group, where our x bar is the mean for all of the elements in our pool. N is going to be the sum of all of the So our total number of elements, and then x sub I bar is going to be the mean of in a particular group. Okay, and so now let's do some algebra. And so the algebra trick that we do, we subtract the group mean and add the group mean inside so it stays balanced. We expand all of this, and so we have a rather complicated expression that looks something like this. Now, what's going to be kind of the real key here is if we notice that if we sum over all of the values and subtract the within group means, that what happens is really that is just 0. And so what I would say would be go back and check the algebra on this, convince yourself that that is actually true. And so where this leads us is that our total variance from our pooled group can be written as two separate sums. And so if we take s sub I squared as just being the within group sample variance for the ith group, then we can write our total variance as the sum of the within group sample variance and then this second sum. So let's see if we can see what that might be. Now the x sub I bars, so those are going to be independent of the s sub i's. Well, that was a theorem that we've again proved, or that we've utilized a great deal before and proved with a fair amount of work. A fair amount of algebraic work, so that's in a previous video. So if you need to review that, go back and check it. Now our total mean, so our mean for all of our groups, we can write that as this expression. And so what that means is because the s sub i's are all independent of the x bars, that and the x bar is a sum of the x sub I bars, then we still have independence. And so what that leads us to is that because we know that the sample variance is for the pooled sample is going to have a chi-square distribution with n minus 1 degrees of freedom. For each of the within group sample, they're going to have a chi-square distribution with n sub I minus 1 degrees of freedom. And so because we add them all together, that will give us a chi-square distribution with the sum of degrees of freedom, which is just going to be our total number of samples minus k, where k is going to be our number of groups. And then because of the independence, that will really allow us to say that that second sum is also going to have a chi-square distribution with k minus 1 degrees of freedom. And so now we're just about there. So if we take u being the sum of the within group variances and v being the second term in our sum, that u has a chi-square distribution, v also has a chi-square distribution, so the ratio of the two chi-square distributions is just going to give us a u and a v, and that's going to have an f distribution with n minus k degrees of freedom for the numerator and k minus 1 degrees of freedom for the denominator. Now, a lot of what you see typically with the analysis of variance is you'll see this discussion of within group sample variances. So within group sample variances, that's just our variances within our individual testing groups, and then you've got the sample variance of the means between groups. So you'll have the within group variances and the between group variances. And so that's our first sum and our second sum. So within group is our numerator, between group is our denominators. And so with that, we've got an F distribution with parameters that are not dependent on the variable that we're looking for, and so we can develop a hypothesis test from this. And so now we can actually turn it over to R, that we've developed some of the theory. Our next video will look at how we actually handle this in R. So stay tuned for that. Hope to see you all in a little bit.